Okay, so we've talked about solving different types of equations, x squared equations, x cubed equations, even some x to the fourth, and maybe higher powered. But what do we do when it comes to an exponential equation? Well, I like to break it up into two separate types. One is kind of a really special type, specialized type, may not happen a whole lot application-wise, but it's good to talk about. So let's call these type 1 exponential equations. And the distinguishing mark on the type 1, what I call type 1, is that the exponential equation has the same base on both sides. A good example is 5 to the 7x plus 3 equals 5 to the 4x minus 5. And so this is going to be an extremely simple example here, but makes the point anyway. So yeah, I've got what makes this an exponential equation? Well, remember, exponentials are ones that have x in the exponent. And so that's what for exponential equations, we're talking about those equations that have x in the exponent. We're not used to those. We haven't come across those, I don't believe, in any form right now. But we've got x in the exponent. So that's what makes these exponential equations. Now, when we have the same base on both sides, that's a very nice case to have because of the nature of exponential functions. We hadn't talked about them being what's known as one-to-one, but because they are one-to-one functions, which means if you've got an x value, it goes to one y value. There's no secondary y value that it could equal like some other functions. Because it's one-to-one, when you have the same base on both sides in an exponential equation, you can just cancel out the bases. Basically what it amounts to. When you have the same base on both sides, you can cancel out the bases. All right? The bases go away, basically, what that means. It only works if you have the same base on both sides. Those bases just cancel out, so that just leaves you the exponents equaling one another. And if you thought about it, that probably makes sense. For this side to equal that side, that's what's going to happen, right? You got to have 7x plus 3 equals 4x minus 5. So the bases, what I'm saying, cancel out. And that's what makes these nice, because then you usually just have a simple equation. Subtract 4x, subtract 3. 3x equals negative 8. Divide by 3. You got x is negative 8/3. Okay. Now, some of them come disguised. I'll just warn you there that they have the same base on both sides, but we'll look at those. All right. So we got 3 to the x plus 5 equals 27. Yeah, so this one is same base on both sides, but it's in disguise, I guess, one way to put it. Because I definitely don't have 3 and then base 3 here. However, what about that 27? That's 3 to the third. I can write that as base 3. So I do have same base on both sides, you see. If I have the same base on both sides, that makes this a very simple problem. Because then the bases just cancel. You got x plus 5 must equal 3 then, right? Exponents must equal. And so it looks like, what, x is negative 2? Yeah. So sometimes you may just have to change the number to that base. What would this one? What would this one be? 5 to the 3x minus 4 equals 1/25. Same idea, isn't it? 25 is a base 5. It's 1/25, so how would I write that as 5 to a power? Well, since it's 1 over 25, it would be 5 to the negative 2. Negative 2. Yeah, 5 squared is 25, so 1 over 25 is 5 to the negative 2. And so then your bases cancel, so you have 3x minus 4 is negative 2, add the 4, divide by the 3. 2/3? All right, now here's about as tricky one as I'll put on these assignments. So I've got 6 to the x minus 2 equals 36 to the 3x plus 1. Kind of tricky because first glance you might say, well, cancel the bases, and you got x minus 2 equals 3x plus 1. The problem is I don't have the same base yet showing on both sides, do I? I got a 6 base here and I got a 36 here. However, 36 is a base 6, isn't it? So I can rewrite part on the right there. 36 is 6 squared. Now, so I'll rewrite that 36 is 6 squared because that gives me the same base. Now, let's go ahead and take care of what this means then. All right, so 6 squared to the 3x plus 1. What do I have to do here with these exponents? Power to a power. You multiply. So this will be 6 to the x minus 2 equals 6 to the 2 times 3x plus 1. I've got to multiply these two powers together. And whichever step you want to do that, it'd be 6 to the 6x plus 2 power. Now I'm in business, all right. Distribute the 2 there, make it 6x plus 2. Now I'm in business because now same base, cancel out. So x minus 2 equals 6x plus 2. And then it's just solve accordingly. I'm going to subtract the x and then subtract 2 to get it negative 4 equals 5x. You can do it the other way if you want. But divide by 5, then you got negative 4/5 equals x. Okay? Sound okay? Question on that one? All right. So that's same base on both sides. Those are very nice. However, as you could probably expect, that may not happen each and every time where we have the same base on both sides, even on these simple ones. It'd be very easy to get this equation where we couldn't do this because we could put in like 25 here. 3 to the x plus 5 equals 25. Well, 25 is not going to be a nice power of 3. It's a nice power of 5, but not a power of 3. So it's very easy to see there that we won't always get this to happen. So that brings up type 2 then. Type of equation. Type 1 is the same base on both sides, and then so type 2 would be different bases on both sides, or not the same base on both sides. That's probably going to happen more often than not if you think about it. Yeah, so just a very simple example would be 3 to the x equals 12. Right? Unlike the 27 when we had base 3, 12 is not a power of 3. 3 to the first is 3, 3 to the second is 9, 3 to the third is 27. So we skip right over numbers like 12 when we go through powers of 3, or nice powers of 3. That's what we're talking about. We have 12 we can't write as base 3. So what are we going to do there? Well, the general rule here, technique, when we have different bases in these exponential equations, is to take the ln of both sides. Now there's a few little restrictions on when you can do it, but take the ln of both sides. That's going to be our go-to technique if we have different bases on both sides. All right, so I've got 3 to the x equals 12. Can't really do our same base thing. So I can't cancel exponents and all that, or bases. So I'm going to take this one and ln both sides, right? Because doing the same thing to both sides, that's usually an okay thing to do. Now, why do this? Well, it's because of what happens over here on the left side. Remember back on we've introduced logarithms here. And we've done it to both sides, so that's what makes this okay, basically. And then, but now with these logarithms, remember property 3 of logarithms? It was log, let's see, we have n log base a of u equals log base a of u to the n. By that property 3 there, on the logarithms, don't I have this on the left side now? Because I have a logarithm here, and it's 3 to a power. What can I do with this power? I can bring it down. And that's good because I'm trying to solve for x, but x is in the power. I've got to get that x out of the power is basically what I've got to do. And so that's what, if I introduce these logarithms, I can do that. The x comes out. Now it's just x times a number equals another number. This is just a number, isn't it? Natural log of 3, and we've got calculators that'll evaluate that. You can do it here, yeah, you can do it right now. But it's just a number. And so I've got x times, how do I get rid of a number that's times the x? I'll make it another step here so we can keep these separate. So bring down the power because it's a logarithm. This is just a number, so how do I get rid of it? It's times the x, so I divide by it, right? X is the ln of 12 divided by the ln of 3. And so I can get
2.26185.
2 point, say it again,
2.26185. 9507.
Yeah, so depending on how many places you want, you can get that value, which does make sense because, like I said, 2 to the second is 9, 2 to the third is 27, so to get 12, yeah, 2 point something makes sense. That's what we need the power of 3 to be. So it makes sense. All right? Okay, what about 500 equals 5 to the 2k? We might be thinking, well, 500, that's a power of 5, isn't it? No. 5 to the first is 5. Well, but 5 to the third is 125. 5 to the fourth is 625. 500 is not a nice power of 5. So this is different bases on both. I can't make this be a power of 5. Okay? So I have to do this other technique, which the other technique is take the ln of both sides. Because that'll bring out the 2k, right? Now, since this is a logarithm, I can take this power and bring it out front. So it's ln of 500 equals 2k times the ln of 5. That's property 3 again of logarithms, kind of in reverse, maybe there, but yes? Okay with that? Well, all right. Trying to solve for k here, find the value of k. I've got 2 times k times, that's just k times 2 numbers, and so to get rid of those 2 numbers, just divide them off. So k, that'll get rid of the 2, that'll get rid of the ln of 5. That's just k then. So it's ln of 500 divided by 2 ln of 5. Now, I do this one specifically because be careful when you enter that into the calculator. If you just took ln of 500 divide by 2 ln of 5, you may not get the right answer. Because I need to divide by both 2 and ln. What I would suggest is put it in ln of 500 divided by parentheses 2 ln of 5. Put in those parentheses around the 2 and the ln of 5, and that should get you the right, well, on mine, actually it's parentheses 500, something like that. Yeah. So ln of 500 parentheses divided by parentheses 2 ln of 5. 1.93. So whatever, how many ever places they want, but be careful with entering that all in there. Okay? All right, now, nice things can happen every once in a while. Not a whole lot, right? But e to the 0.05x equals 90.2. So again, not going to be able to make those same base, so definitely want to ln both sides here, right? Take the ln of both sides. What you do to one side, do the other. So we're going to ln both sides. And this is why typically we pick the ln. We could do this. We could take log of both sides. It would work. If we did log of both sides, this would work out. However, because of what we'll run into sometimes, this one in particular, that's why I choose always go with the ln of both sides. All right, so what happens? Well, that comes out because it's a logarithm. I can bring down the power. And this is where the nice thing occurs. Well, I guess you don't have to recognize it, but do you see one thing nice here? ln of e. Yeah, ln of e, we mentioned that previous discussion there. That's 1. That equals 1, so this is just 0.05x equals ln of 90.2. Simplifies down really nicely. So all I have to do then is divide by 0.05x, I mean 0.05. So do ln of 90.2 divide by 0.05, 90.04, approximately, about. Okay? All right, now, a couple of little fine details here. So I've got 40 e to the x minus 7 equals 300. Okay, so what you're going to want to do on this, the little flip on this one is I've got 40 times the exponential. Previously, I just had the exponential equals a number. Here I've got 40 times the exponential equals 300. So a couple ways you could go, but probably the way you want to go on this is to get rid of that 40 first. Isolate, we need this isolated. The exponential first. In other words, get rid of the 40 first. So that would be, how would you get rid of the 40? Divide it, yeah. Just divide off the 40 first. So I have e to the x minus 7 equals 300 divided 7.5. Now it's set up very nicely. ln both sides. That'll allow me to then bring down the power. X minus 7 times the ln of e equals ln of 7.5. Well, the ln of e there is just 1. And so this is just x minus 7 equals ln of 7.5. Right? Now, all I have to do is add the 7. Now, one other note there. Is that ln of 12.5? That is not the ln of 12.5. I can't add these two together. This 7 is just separate. So just do ln of 7.5. And then add 7 to that. Just looks like it's 9.0149. Blah, blah, blah. How many ever places we want there. Okay? All right, this one is somewhat similar. 5e to the 2x plus 1 equals 20. What do you think we got to do there first? Get rid of the 1 and the 5, right? I need the exponential, I need to isolate that. So I've got a plus 1 and I got a 5 that I don't want on this side. I only want e to the 2x on this side. So yes, subtract the 1, 5e to the 2x, then equals 19. Divide by the 5. You get e to the 2x equals 19 fifths. You leave it that way, or 3.8. Want a decimal there? Now we ln on both sides. ln e to the 2x, ln to 3.8. That'll allow me to bring down the power, so that'll be 2x times ln of e. What we like when we get the ln of e, because that's just 1. So it's 2x equals ln of 3.8. Divide by 2. ln of 3.8, divide by 2. 0.6675. How many ever places we need? Is that okay?